Welcome to the perspective unit of week 3, in which we do two things. First of all, we answer frequently asked questions that typically come up when we teach how to build memory systems, and we use this opportunity also to say all sorts of disclaimers about various things that we covered during this week. So the first question that I'd like to talk about is as follows. During this week, we used flip-flop gates without actually building them. We treated them as black box abstractions. What does it take to actually build a flip-flop? So Noam, maybe you will take this question.
In many courses on computer hardware, students are taught how to construct flip-flop gates from basic NAND gates. Once that is done, they continue with the usual thing, which is also done in practice, of a complete separation between the way you use combinatorial circuitry and the way you use sequential circuitry. But at the beginning, they do construct a flip-flop from basic NAND gates. In our course, we decided to skip that part and really focus on, at the beginning, on the difference between the combinatorial point of view and the sequential point of view. Nevertheless, it was probably a good idea to see the main trick: how can you get NAND gates to remember anything? And this is as follows. So the basic idea is to take two NAND gates and connect them in a loop. So we have here two inputs, each one feeding into one NAND gate, where the other input of the NAND gate is fed the output of the previous NAND gate. Now normally, this is a no-no. You're not supposed to connect combinatorial gates in a loop. In fact, the hardware simulator we give in this course explicitly forbids it, and this is done for pedagogic reasons. Now let us see how this thing works in this particular case where it's actually used. So normally, this kind of circuit is supposed to be used when both of its inputs are set to 1. Now in this situation, we don't know what this NAND gate will do because we don't yet know what this input is. So because we don't know what the previous value, or the previous, there's no real previous here, but we don't know what the value here is, so we don't know what the value of the input is, and we don't know what the value of the output is, so at the beginning we know nothing. But then what happens once we take one of these inputs and turn it to 0 for a while? At this point, because this is a NAND gate, we can immediately see that the output of this gate is going to be 1, independently of what this question mark was. Once this is 1, we know that this is going to be 1. The output of this NAND gate is going to be 0. Now, once this is 0, we can fill in this question mark and make it 0. And then we have two zeros that are output 1, and everything is very stable here. Now, so what's so interesting about it? Now let us see what happens when this input goes up back to 1. In this case, nothing changes. Because this is a NAND gate, this output remains 1, so these two remain 1, this remains 0, this remains 0, and everything is completely stable. So somehow, we remember now that the last input that became 0 was this one, because we have a 0 here. Now let us see what happens when something changes. For example, where at a different time step, at a future time point, this one becomes 0. Now once this becomes 0, this immediately, the output here becomes 1. The output here becomes 1, this becomes 1, the output here becomes 0. The output here becomes 0, this changes to 0, and again, this stays 1, so we're again stable. Now, when we turn this back to 1, to the normal state of 1, everything remains the same, because 1 NAND 0 is still 1. So everything is completely stable in this new situation, which is different than the previous one, because now we have 0 here and 1 here, while previously we had the opposite values. So now we remember that the last input went down to 0 was the bottom one. And this kind of behavior allows this loop, basically, to remember the last input wire that went to 0, and it's stable in each of two different situations. That's why flip-flop is called, that's why the name is flip-flop. It can either flip, so we have 0 here and 1 here, or flop, that we have 1 here and 0 here. In any case, a momentarily change in the input changes the output for the future. Now, this is just the basic functionality that gets you to remember stuff. Of course, when you want to actually use this in a nice flip-flop, like we have used the D flip-flop, you first of all need to put something around it which actually makes sure that the inputs are behaved nicely and choose which one of the outputs you want to take. And also you need to actually somehow separate what happens within one clock cycle from what happens in the next clock cycle. And that is done usually by putting another one of these and driving one of them with a clock and the other with the opposite of the clock. But we don't want to get into these details, but just to show the basic idea, which is quite surprising, how you can remember something even though you only have an AND gate.
So thank you, Noam, for this explanation, which indeed was somewhat intricate. And a follow-up question that typically comes up is that is NAND gate the only basic technology for building memory systems today?
Well, Shimon, the truth is this is not the only way to construct flip-flops. In many other cases, flip-flops are constructed using some basic physical properties of the underlying solid-state physics of the devices that are used for this kind of storage. Now, this kind of the details of such devices and how they remember anything is really physics or electrical engineering and not something that we touch in this course.
Okay, so here's the next question. During this week, we built a memory device which you called RAM. Is this the only memory device that computers use? Well, the answer is definitely not. Computers use various kinds of memory devices, of which the RAM is indeed the most important one. The RAM, which stands for Random Access Memory, stores both data and instructions, and it is a volatile device, meaning that it depends on an external power supply. So once you disconnect the computer from the power supply or turn it off, the contents of the RAM is effectively erased. So in addition to the RAM unit, computers also typically use another device called ROM, which stands for read-only memory. So the ROM is not only read-only, it is also a non-volatile device, unlike the RAM, which means that it maintains its current contents a long time, over time, and it does not depend on an external power supply, which makes it very convenient because the ROM is where you want to put the programs that have to work when you turn on the computer. You know, this is what is known as the booting process. So when you boot up the computer, the program which is stored or pre-stored in the ROM starts running, and this program normally initializes all sorts of things in the operating system and in the computer. Actually, not in the operating system, but in lower level code. And the next thing that the ROM does is, or the program that resides in the ROM does, it loads from the disk the startup code of the operating system. And then finally, we begin to see some windows on the screen and the computer sort of comes alive. Another technology which you've probably heard of is called flash memory. And flash memory is a technology which actually combines the good things of both the RAM and the ROM. On the one hand, it's a read-write memory. You can both read and modify its contents. And at the same time, it does not depend on an external power supply like the ROM. So once you turn off the computer, the contents of the flash memory remains intact. So we talked about RAM, ROM, flash. Another kind of memory which you normally encounter is called cache memory. So the question is, what is cache memory and why do we need it?
When one actually builds a computer, the memory is going to be a pretty costly part of the whole system. And as you can expect, there are many different technologies for building memories, and the faster the memory is, the more expensive it usually is. The larger the memory, the more expensive it usually is. So an architect, a computer architect, is always faced with a trade-off of, does he want to put more money into the memory and make it larger and faster, or does he want to get a cheaper memory and maybe put the money more in the processing unit? A usual trade-off is to have a large, cheap memory, maybe slow also, and a very small, expensive, fast memory. and try to make sure that what the data that is very often used by the processor reside in the very fast memory, while the data that is only rarely used resides in the slow memory. This way you get the speed of a very fast memory while you have the size of a very cheap memory. To do this correctly is a very intricate art, and today computers usually have whole hierarchies of caches. These are called caches. The small fast memory is called a cache. Hierarchies of such caches that are faster and faster and expensive and more expensive and more expensive and smaller as they get closer to the processor. And doing that correctly allows you to really get amazing, effective speed of a very fast memory, even though there is only a very small fast memory and a very large slow memory.
Okay, so thank you, Noam, for this explanation. And indeed, from a physical standpoint, we have many different kinds of memory units, and we discussed some of them in this perspective discussion. And yet, it's important to emphasize that from a logical perspective, all these different memory systems, you know, the RAM, the ROM, the cache, and so on, they all look alike. They all behave like a sequence of registers which are addressable, and we can access any one of these registers and do something with the bit contents of these registers. So everything that we said during this week is completely applicable to every kind of memory that we discussed in this unit.